how we can establish secure secrets federation and like dispatch secrets from a central control plane to a edge store locations based on like certain primitives have been established. So for this architecture, I'll use SPIFFE and Spire and also VMware Secrets Manager, and I'll explain through how the day 0 setup and day 1 setup happens. And this is like a demo proof of concept, so I am taking shortcuts in certain parts, like I am, for example, calling like direct kubectl commands or like generating secrets off cycle rather than letting a controller or an operator do it. But technically it is programmable, so whatever I display or whatever I explain can also turn into like a Kubernetes native construct. It's just not here because like it hasn't been implemented yet. So let me show you what I have. So I have 4 servers. I have shown this setup before, but like let me go through it again. I have 4 servers. The top one, which is this one, this is Diablo, which is the main central control plane, and the bottom 3 are a Mephisto, Baal, and Asmodan. I missed the orders. I guess Mephisto is the center one, Asmodan is this one, and Baal is that one. But regardless, it doesn't matter. In our scenario, what happens is these edge stores are like depicted to be locations that are farther away on the edge, away from the central single pane of glass control plane. So what they will do is they'll do polling. So they'll poll the main control plane regularly, and they are going to like fetch critical data. And since they are fetching critical data, these will be done through MTLS, and that MTLS will be done by SPIFFE Federation. But MTLS is not enough when you are transmitting secrets, because lots of lots of standards require, and like common sense also requires, that when you are transferring a secret, you need to encrypt that secret as well. Even if it's MTLS, secrets should not be pushed unencrypted in transit, and they shouldn't be stored unencrypted on disk as well. So whenever you are storing something sensitive, you need to encrypt it. Essentially, the only place that a secret can be decrypted or not, can be plain text is in memory, because Linux and other operating systems have like memory protection and memory boundaries. But other than that, anywhere you store a secret, you need to encrypt it. So the control plane will provide the secrets, but you'll see that those given secrets will be encrypted several layers to make it secure. So that is the overall interaction. Edge clusters will poll, the central control plane will give the data regularly. But before that, I want to explain the setup. So to make things secure, there's some level of human interaction, because if you automate everything, then the problem of establishing the initial trust, which is a good, well-known problem, becomes an issue. So what happens here is, like, I am assuming that in the control plane, we are bundling some kind of software. It can be a like OSI image and OVA image, or something that can be deployable on a hypervisor. So what the control plane does is, on behalf of customer, it creates an image, and both on control plane and also on edge stores, there will be VMware Secrets Manager. So during this process, we also add VMware Secrets Manager's root key, and also a bunch of other configuration material that might be required for this edge store to it. And then we bundle that OVA with the config file, and this human operator has a encryption key that only they know. They will encrypt this entire bundle with their encryption key. So this thing will be totally encrypted. So over whichever secure mechanism, it can be either like a secure portal, or it can even be like you can physically deliver the product to the user through like snail mail or like USPS or something. So regardless of what the mechanism is, there is a off-the-band way that this entire bundle, this thing is delivered to the human operator. So when the human operator gets it, they will decrypt the bundle, and then they are going to provision that thing, likely with an automated script, to the edge store. So in the end of the day, when this happens, let's say this red thing is vSecond root key, not this one, sorry. This red box is VMware Secrets Manager root key. Both control plane and edge store will have the same VMware Secrets Manager root key, and nobody else will have that knowledge, assuming this transfer is secure. And there will be ways to rotate this root key too, but I'm not talking about that because that's a separate problem set to sort out in itself. So this is the day 0 setup. And given that edge store, not that one, sorry. Given that the edge store and also the control plane has VMware Secrets Manager root key, and also given that we have established a SPIFFE federation between the edge store and the control plane. So we have two assumptions here. One of them is there's a pre-existing SPIFFE federation relationship, and secondly, edge store and control plane are sharing in secret the same root key, and that root key hasn't leaked. So, which means edge store, because of the federation relationship, can request its SWIT, which is an X509 certificate from the SPIFFE workload API, and it gets an SWIT from the SPIFFE workload API. And similarly, control plane using SPIFFE workload API also gets its own SWIT. So these two SWITs, let me like depict them with these yellow boxes. So red boxes were secrets, yellow boxes are red boxes were root keys, yellow boxes are SWIT. So both of them have their own certificates, which means from this point on, they can establish MTLS here. So edge store will create itself a new key pair. This is different than these SPIFFE given X509 certs. It will create a one-time private public key pair to be used in this interaction that we'll see. And similarly, control plane will generate its own key pair as well. This is to establish perfect forward secrecy. So these key pairs will be only used once for this interaction, and for another polling cycle, it will be the system will use another key, which means the older key will be unusable because it won't matter anymore. So that's that thing. The reason that we can do this is because the edge store, like this, where is that one? This polling operation, this post is infrequent. Like it's maybe days, maybe hours, but it's not edge store is like hitting the control plane every 5 seconds. So there's time between them. So it's not CPU intensive. So it can be CPU intensive once. I can dump lots of cryptographic algorithms in it, but it won't impact the end system performance because the polling is like less frequent. And it should be, because we are transferring secret. Like you don't transfer secret every second, essentially. It's like more like synchronizing secrets whenever you need them. So once it posts, once the edge store posts its public key to the control plane, what control plane does is it will first extract the SPIFFE ID from the edge store's SPIFFE certificate, this yellow one, and then it will verify the SPIFFE ID to ensure the authenticity of the edge store. Then it will create a key pair itself as well. And then it will also create a AES key to encrypt the payload it's going to send to the edge store. And then it will encrypt the AES key with Edge Store's public key, the public key that it created here. This way, the AES key cannot be compromised unless somebody knows the private key of the Edge Store, and the private key of the Edge Store is unlikely to be compromised because it's just being created. Nobody knows it yet. So that's that one. Then after that, this control plane will talk to VMware Secrets Manager to get the secrets that the Edge Store wants or needs. It will encrypt the secrets with the AES key because the secret that we get from VMware Secrets Manager is encrypted in itself, which means it's like a big chunk of text. You cannot just encrypt it with the key of let's see. Let's give me a second. The camera started zooming at me. Okay, this is better, I guess. So the thing is, the payload that comes from VMware Secret Manager, since it's encrypted, it has a large block size, so you cannot just encrypt it with a regular private key, public key pair, X509 key pair. You need AES to encrypt it, but I cannot send the AES key, which is an AES key, directly. So I am encrypting the AES key with the key of the public key of the sender, which is like similar to how HTTPS works in a sense. And to ensure authenticity as an additional layer, we are also signing the encrypted data with the key of the control plane's private key, which then can be verified by the public key of the control plane that we'll be sending here, essentially. So as a response to the Edge Store, we are sending the encrypted data, the signature to verify the authenticity of the payload, and also the control plane's generated public key. This public key is also generated on the fly right now, so it's really hard to get it because it's being dispatched through an MTLS connection that has already been secured, and this public key doesn't have a precursor. It is just being created at runtime right now, essentially. This gives like a additional level of security to the entire interaction. So what happens here is we verify the signature, and if there's anything that feels fishy in this interaction, we just exit, panic, don't store, cancel the entire flow. I am just going through the happy path, but assume that there is also unhappy paths that when these fail, things just break and we don't do this key exchange whenever we feel that this thing is suspicious. So we verify the signature, then we decrypt the edge host's private key so that we can decrypt the payload. Then we decrypt the payload with the AES key, and we still have a encrypted secret at hand, and we need VMware Secrets Manager's root key to decrypt that secret. So for security, this Edge Store doesn't have access to VMware Secrets Manager's root key, and it shouldn't. VMware Secret Manager itself has access to its root key, but the Edge Store can still say, hey, I have this key, I have the secret for this workload. I don't know what it is because I cannot decrypt it with the root key. Only you have the root key with Secam. So can you please register it for this workload? The workload can receive it because it knows how to talk to your APIs, but I don't. So it will just send that encrypted payload without even knowing what's the content of that secret that is destined for this workload, essentially. So Secret Manager stores the secret in itself, and then the consumer, which is it can be any kind of workload that needs that secret. There are several ways that the consumer can request the secret. It can just bind to a Kubernetes secret if the secret manager is programmed to create Kubernetes secrets on behalf of a secret register to it. Or it can, the better, more secure way is it can request its secret through VMware Secrets Manager's SDK over MTLS. This is again SPIFFE MTLS. It will ask for the secret, and then and only then VMware Secret Manager will send the decrypted payload to the workload. So as a summary, let me zoom out a little bit. Can I zoom out? Let me see. It should be. Where's the zoom out? Here. So if I zoom out, so this is control plane, this is edge store, like there's lots of exchange going on here. And until the secret comes here, no one in this interaction can get the actual value of the secret. It is only meant for the consumer workload, and it is only dispatched in plane through MTLS to the consumer workload. So it gives a several layers of security, because there is at least double, maybe triple layer of encryption until a secret goes across the wire and from like this edge store, from the edge store comes like all the way to the workload. So that's how this works overall. So I'll just quickly go through the source code, and then I'll try to show it with a live demo, praying the demo gods that things will work. If it doesn't, like we'll see, but let's see how things go. So this is the server code. I'm not going to go too much, like I'm not going to parse the code too much. And for the sake of the argument, I'm just loading the secrets from a file system. I can just show you how that secret looks like. Let me go here. CD workspace, CD data, cat secrets.json. Like you see, this is encrypted and also base64 encoded. So don't assume like this is decodable just because it's base64. This is encrypted and then encoded. Therefore you can still think these are secure and stored securely at rest, and the only way to decrypt them is to get the root key that encrypted this. So but like normally we won't be loading it from file system. We are loading it from the disk, just for the sake of this proof of concept. It will ideally be pushed through some sort of either controller and interaction of this workload with VMware Secrets Manager. It might be stored in a database, or it can be something else. But like regardless, we assume that there is a way to fetch that secrets. After that, I'll skip this workload API prelude. We are creating a secure MTLS service that the other party, this edge cluster, will talk to us, and that security will be established by SPIFFE Federation. I'll show that bundle exchange at least in the server logs as well. This is the server part in a nutshell. In the client, like to show things work, I'm polling every 10 seconds. Ideally, this polling interval, like I said, will be like days, probably, depending on the use case. But like it works with a 10-second poll in a relatively minimal demo cluster as well. So even if a relatively frequent poll with a relatively small number of nodes works at scale without any problem. Because like when the number of nodes are small, there is no pressure in the main server. And if there is, you can always like do some horizontal scaling. Essentially, you can distribute the cryptographic compute task. So what the client does in this every run loop essentially is, again, it establishes some MTLS connection with the server. I'll skip that part for the sake of brevity. But these source codes are all available at github.com VMware Tanzu /secrets manager. Let me actually write it down here. HTTPS github.com, VMware Tanzu, secrets manager. So like you can go, there's an examples folder, and like on it there is like workshops Federation folder. So, and I am like going through the examples in this folder at the moment. Like as you see, it is where is that one? It's down here, this folder that I'm talking about. So you can just go and see the source code on your own as well. So there's some additional handshake, and eventually it does, what I explained, it does essentially in the client part, and it will get the secret in encoded form, and it will register the secret to VMware Secret Manager. And to register the secret, again, I'm faking and doing like a kubectl exec kind of a command using the Kubernetes REST client set. Ideally, this should be done through VMware Secret Manager's MTLS RESTful API. But for the sake of demo and for the sake of saving time and for the sake of keeping the code brief, I just like hacked around it essentially, and that's that part. So when we get the secret eventually, and after we register the secret that we get to VMware Secret Manager safe, and let me also explain these commands. So it says register a secret for this workload name, and the secret value is whichever encrypted value comes from this interaction that we had so far. And this -e flag says that the secret that I have is encrypted. I don't know the contents of it, but you know how to decrypt it. So I'm sending it in encrypted form. Just decrypt it before registering it to the workload. So VMware Secret Manager will handle that part. It will store decrypt this text, store it in its key store, and it will dispatch the secret to the workload that needs it whenever there is a need, whenever the workload pulls it through the SDK eventually. And to have a shortcut, because this is a demo again, what I did is I kind of emulated that workload in this server, in this client as well. So what I did here is I am using, let me show it here, VMware Secrets Manager Go SDK, and there's this sentry.fetch command, which just gives me essentially the secret. So this rest.data is the decrypted secret that the workload can use in however way it likes to use. When I do the demo, it will be more clear, but I just wanted to just quickly go through the source code to show how things go essentially. Before I start the demo, let me go through the Spire server logs as well. kubectl get po-and Spire server -0. Spire server -0-f. This is what Spire server is doing in the control plane, and I'll do the same on the edge clusters as well. Just give me a second. Not getpo, sorry, kubectl logs. Let me copy this one too, so I'll paste it to the other nodes as well. So let me paste and I'll talk about it later. Enter, and enter this one. So what it does is it's exchanging trust bundles with these 3 edge nodes in a hub spoke manner. So if you see the bundle that is refreshed, let me choose a different color. The bundle that's refreshed here is only for Diablo, and this folk is Diablo. So all of the edge nodes are just exchanging their bundle with Diablo, but Diablo is exchanging its bundles with, let me highlight here, Mephisto, Baal, and Asmodan, which are these 3 folks essentially, which establishes like a hub and spoke topology. So which in this case, this server is the hub and these 3 are the spokes, and there's like MTLS connectivity between these, but not between the spokes. So the hubs and spoke can talk and can pull, like these spokes can pull the hubs, but like this kind of interaction is not allowed because there's no federation relationship between them, which also makes sense because these edge locations have their own trust boundaries, and you likely don't want, I don't want to give brand names, but for the sake of giving a brand, you don't want your favorite coffee shop talk to your favorite discount store, talk to your, I don't know, favorite electronics store. So that's why they have their different trust domains, but still they can call the same home because we have established a federation relationship here. So that's how it works. I'll close the logs that shows the Spire servers are exchanging bundles to maintain a secure MTLS trust relationship between them. So on the main server, I'll go to CD. Let me go to my home folder, the workspace, VM secrets manager, then examples, then workshop SPIFFE Federation. Then I'll go to clusters. This cluster's name is Diablo. Let me double check. It is Diablo. So I'll go to Diablo. In the Kubernetes folder, I have control plane server. So to show, and I'll just show it on this control plane. It is the same in edge nodes as well. kubectl get pod Spire server. I have a running Spire server. kubectl get pod Spire system. I have a Spire agent on it. kubectl get pod vsecum system. I have VMware Secrets Manager on this machine up and running as well. So here I have the deployment manifest for the control plane server, and on the nodes I have client applications deployment manifest as well. I'll just deploy it. You can check the source code at your own leisure, but let me just show the deployment for the sake of completeness. Vim deployment YAML. So I'll just go a little bit downwards. It has it's typical deployment. It has labels and images and volumes. The only thing that makes it a little bit different is this SPIFFE, this SPIFFE endpoint socket, which makes it talk to the SPIFFE workload API. But other than that, it's pretty boring deployment, to be honest. So I'll just apply it, kubectl apply -f, enter, clear, kubectl get po. I have a server running. I'll just tail its logs to see if it's up and running. For starters, kubectl logs control plane server -f. So yeah, it started listening through MTLS. So let me just move these a little bit, make these two a little bit shorter, thinner, and I'll elongate this one so that at least I can show one client in more detail and the others will reflect, mirror each other anyway. So I'll go to this is Edge Store, so see the clusters, and this cluster is Baal. I'll do the others as well. So where am I? See the Mephisto. What? So this is clusters, Mephisto. Where am I? See the clusters, Osmodan. So I am in the cluster folder. So I have Kubernetes deployment manifests for the Edge server. So I'll go to the K8s folder. And again, you can go to the GitHub repository and see the entire source code. I'll just briefly go through some of it, but I won't cover everything essentially. So here I have Edge store. I'll just go through deployment, Vim deployment YAML. Again, it's relatively typical deployment. It has an image that comes from a local registry. I have defined a bunch of environment variables. There will be ways to streamline this so you don't have to define like 10 different environment variables. Right now it is how it is, but there is an open issue that just specifying the trust domain would be sufficient and you won't have to define these like regular expressions and whatnot. But right now it is how it is. But other than that, this is again a typical deployment that is talking to a SPIFFE agent socket, but nothing else. Let me quit this one. kubectl apply -f. I'll do the same in others as well. Where am I? I'll go to K8s, Edge store, kubectl apply -f. And you see like we started receiving connections from Baal already. And the next one will be Mephisto. And the next one will be Asmodan, hopefully. kubectl cd K8s. Where am I? cd Edge store. kubectl apply -f dot. Okay, let's see. I have Baal, I have Mephisto, I'm waiting for Asmodan, it will come eventually. Yeah, and I have Asmodan, so they are doing more or less the same thing, so I'll just like focus on the logs of the Baal, because it's the larger one. I'll just move these two aside. Actually, just let me like tail the logs, but I won't focus on them. I'll just tail them to see that they are also running. Get po. I have this Edge store. kubectl logs Edge store -f. Follow this one. kubectl get po. kubectl logs -f. I'll push them all the way here because they're identical. You don't need to see them all. kubectl get po and kubectl logs this Edge store -f as well. So like it's not displaying all of the details because like lots of them are like key exchange, secrets sharing, and things like that. But what happens is like after some verification of the signatures and decryptions of keys and getting stuff, the Edge store eventually gets its secret, but that secret is still undecipherable for the Edge store itself because it's encrypted with VMware Secrets Manager's root key, which the Edge store doesn't have it. It cannot directly get it. But in this demo, just for the sake of the demo, we have doubled the Edge store as a workload as well. You don't have to, and typically you shouldn't need to, and you should keep it separated for the sake of, separation of responsibilities, keeping things secure, separation of concerns, however you call it. But if this Edge store is also a workload, then it can talk to VMware Secrets Manager APIs through either Go SDK or using a sidecar or directly consuming a secret that the VMware Secret Manager has minted. And by talking to the vSecOm API, I am able to get the secret in decrypted form. And in this case, I can see that the secret is for Baal, and it is asking me to create a admin password in the VMware Secrets Manager namespace, default namespace, and the contents of that admin password should be this one. What we have established is we have some secret material in this control plane, and we were able to securely double encrypt it, and dispatch it to this location through SPIFFE MTLS as well. So it's a fairly secure way of dispatching it, because even if the secret is exposed, you will still need a additional root key to additional root key to decrypt this payload. So from something turning from this to this requires a separate level of interaction, which nobody has the knowledge of that key. So, but overall, this kind of finalizes what I have to say. Let me think about it, if there is anything else. Yeah, that's overall, that's what happens. So we were able to establish MTLS connectivity by using SPIFFE Federation, and then we were again able to dispatch secrets dynamically to workloads, and we were able to let the workloads receive that secrets and consume them without having to restart the workloads themselves. So it's a